Hello, this is Edward from Enfield Physics Tutor. Today we're going to look at circular motion with an emphasis on the radian and angular velocity. Circular motion is important because it also forms the foundation for everybody's favourite topic, simple harmonic motion. Let's consider a circle of radius r, and we're going to add a segment around the edge of the circle of the same length, which you can see in red there. So that is also of length r. We can repeat this process moving around the circle with segments of length r, and what we find is that we will end up with 6 and a small bit left over. Considering one sector of length r, we can define this angle theta as being 1 radian. Imagine how long the circumference is. Well, I'm sure you know it's 2 pi times r. In other words, that means that r fits around the edge 2 times pi, i.e. 6.28, times. Theta here is defined as being 1 radian. This is the angle subtended between 2 radii when the distance between those 2 radii is 1 radius. It's therefore fairly simple to work out what theta, 1 radian, is in degrees, since going round the circle in degrees is 360 degrees, and it's also 2 pi radians, so therefore we can set them equal. This means that 1 radian is simply 360 divided by 2 times pi, or 6.28, meaning 1 radian is around about 57.3 degrees. We are now going to consider the velocity of the object as it rotates. You may recall that velocity is a vector having size and direction, and since the direction is constantly changing as it rotates, so is the velocity. However, we can get the instantaneous velocity, i.e. the velocity at a point, by drawing a tangent to the circle at that point. We can of course repeat this at any point we like around the circle, and it quickly becomes apparent that the velocity is changing constantly, although the magnitude remains fixed. We're now going to move on to angular velocity, which is a measure of how many degrees or radians an object rotating turns through in a given time. This is given the symbol omega, which as you can see is not the same as w. This is defined as being the angle rotated through over the time taken, or perhaps better still, change in the angle over the change in the time. This is normally measured in radians per second, but not always. I sometimes think we could teach large sections of physics at school by just having a day out at an amusement park. Here's a Ferris wheel which we're going to use to see why angular velocity is so helpful. I've zoomed in now and added a radius and also assigned a direction of rotation. Now consider 2 points along that radius that we just added. So obviously these 2 points are going to move around together. If they didn't take the same time to complete one rotation, then the Ferris wheel would just fall to pieces, wouldn't it? Therefore we can say that both green blobs have the same angular velocity. It doesn't matter where they are on the radius, since they take the same time to go round once. The outer blob clearly has a longer journey than the inner blob because the radius is bigger, and therefore, given that they both take the same time to go round, the outer blob must have a larger magnitude of instantaneous velocity. Therefore, we can conclude that for our 2 blobs sitting on the same radius, that their angular velocity is the same, but their instantaneous velocity is different depending on how big the radius is. Last thing we wrote down then was that omega equals theta, the angle moved through, divided by the time taken. We now want to get some perhaps more useful formulas for that. So remember that in one turn, the complete angle that we've moved through is 2 pi, because there are 2 pi radians in a circle. And if we divide that by t, how long it took to make the circle, then that will be the angular velocity. But remember, small t in this expression is actually called the period being the time for one turn. Therefore, we can rewrite this expression as omega equals 2 pi over t, capital T that is, for the period. Of course, don't forget theta has to be in radians for these formulas to work. Now, hopefully you can recall from earlier work that 1 over the frequency is the same as the period. Such a massively useful formula. Therefore, we can rewrite omega as being equal to 2 pi f. Lastly then, for this video, let's derive a simple expression for the instantaneous velocity. Well, we all know that speed or velocity is distance over time, and we've also seen that in one rotation that distance is 2 pi r. And we also know that the time for one rotation is capital T, the period. Therefore, substituting in speed is distance over time, we quickly get that speed is equal to 2 pi r over the period t. Now earlier we saw that 2 pi over t is equal to omega, as long as t is the period, that is. Therefore, the speed at any point is going to be equal to omega r. And this of course means we can say that the instantaneous velocity at any point is also equal to omega r.